some of the first things that are recognized as the building blocks of today's view are called the mass laws. And the first one I want to mention is the most obvious one. It is that the total mass of substances involved in a chemical reaction doesn't change. Whatever reactants you start with, their mass is the same as the mass of whatever you finish with, your products. Reactants go to products, total mass doesn't change. This is called the conservation of mass, nothing gets lost. Okay? That's assuming that you don't spill any product. Okay? We'll talk about that later. Now, it is true that the number of substances may change. You may have one substance that forms two, or two that form one, or three that form six. There are many different possibilities there. But the total mass, when you're finished, is the same as the total mass when you start. So if we have a hypothetical reaction, reactant 1 plus reactant 2 goes to one or more products. What we're saying is every bit of mass that's present in reactant 1 and reactant 2 shows up over here. Nothing gets lost. So that's a laboratory observation, right? That's something that you would have to do measurements to have discovered if you discovered this law. You would measure masses and then measure product masses and make sure that your measurements corresponded. So you would measure out reactant 1 and reactant 2 and determine the total mass. Then you would look at the products when the reaction was done, look at that total mass. Let's suppose that you were interested in how can we get rid of the carbon dioxide that seems to be building up in our atmosphere. Well, that process is one of great interest. It's called sequestering carbon dioxide. And there are many chemical ways to do it. One of them has to do with the reaction of calcium oxide, simple chemical compound with carbon dioxide. Under some circumstances, those two will react to make calcium carbonate, which, if there are any geology majors in the neighborhood, know that that's one of the components of limestone, right? Any geology majors? A few. Good. Welcome. Glad you're here. Limestone. Now, if this reaction took place, then what we are saying in the law of conservation of mass is the total mass of calcium oxide plus the total mass of carbon dioxide would be equal to the total mass of calcium carbonate. What if some of the carbon dioxide, what if some of the calcium oxide didn't react and it was left over? Would the law apply? Would it still apply? Sure it does. Sure it does. If that amount of calcium oxide that doesn't react will be left over here, and we would count its mass as well. So the law of conservation of mass is a fundamental part of how we look at chemical reactions. In terms of formulas, calcium oxide is CaO. Carbon dioxide, of course, is CO2, and calcium carbonate is CaCO3. So under the right circumstances, one of these and one of these makes one of these. But even if it doesn't, the mass of each of these two will sum up to the mass of whatever's over here, whether it's calcium carbonate and CO2 or calcium carbonate and calcium oxide, doesn't matter. The mass doesn't change. Ideally, 56 and change grams of calcium oxide reacts with 44 grams of CO2 to give 100 and change grams of calcium carbonate. Well, one of the questions we're going to be answering is why is that? Why do these two react in that way to make this with nothing left over? That's a different question. We're asking now, why is the sum of these two the same as that number? And in fact, of course, it is. Let me go back and be sure you had a chance to ask questions. Are there any questions on this pretty simple idea we're starting with? Okay, if you're comfortable with it, then I will go back to the next page. And I want to look at this problem. Now let's look at this. This is a reaction of magnesium and nitrogen gas. Nitrogen gas is one of the 7 famous diatomic molecules. It comes as N2. Magnesium reacts with it to produce magnesium nitride. It happens that the formula is Mg3N2. We're going to talk about how that comes about, why it is, later. But that's, again, a different question. Right now, our question is, what mass of dinitrogen is left over when 0.225 grams of magnesium are heated with 0.331 grams of dinitrogen and 0.3114 grams of magnesium nitride form? Okay, our goal here is to look at the quantitative relationships that we have based on conservation of mass. Let's look at them. We don't have to write a balanced equation. We have 2 reactants, we have a product. So we can, and I really like to do this, we can write down sort of what the start is here. At the start, what do we have? Well, the problem says we have 0.225 grams of magnesium, and we have 0.331 grams of dinitrogen, and we don't have any product because the reaction hasn't happened yet. We're at the start. Okay? Now, when the reaction does occur, the problem tells us we get this much magnesium nitride and that all the magnesium was consumed. So at the end, the magnesium mass will be 0 because it says it was all consumed. It's all gone and it's present in this product. Okay, so at the end, what do we have? We have 0 grams of magnesium. That was all consumed. We have an unknown number of grams of nitrogen. This is what we're going to determine. What mass of dinitrogen is left over? And we have 0.3114 grams of the product magnesium nitride. Okay, now I think you can see a way into this. Let me suggest it to you. This quantity right here consists of magnesium plus dinitrogen. And we know that it contains 0.2250 grams of magnesium. We don't know how much nitrogen it contains, but it seems reasonable that if we take 0.3114 grams of the product and subtract the amount of magnesium we know to be there, the rest is going to have to be nitrogen. Okay? So 0.3114 grams of magnesium minus 314 grams of magnesium nitride minus 0.225 grams of the magnesium means that we actually used the difference between the two, 0.0864 grams of dinitrogen. That's how much we used to make this much product, and we know that because of these two numbers, 0.3114 minus 0.2250. Does anyone have a question about that? Is it clear? Okay, good. Now, at this point, we're not home, but we're getting closer. If we know this mass of nitrogen was used up, and we know this amount of nitrogen was present at the beginning, the difference between the two will be how much is left over. So that's pretty easy. 0.5331 grams of dinitrogen at the start minus 0.0864 grams that were used up, as we just showed you, leaves 0.4467 grams of dinitrogen left over. Does anyone have a question on the process? Yes, go ahead.
When do we balance the equation?
You need a balanced chemical equation when you're going to predict the amount of products that will react with one another, for example. Here, we're just given this reaction, and clearly this isn't what we call a stoichiometric reaction where we would use balanced equations. There is an excess here, and the excess is of dinitrogen, and that's what we're looking at. Is there another question here? You comfortable with this? All right. you should know how to use the law of conservation of mass to answer questions like this, and there's some on the homework for you. Now, that's the first of three mass laws that I want to talk to you about. It's the most straightforward. The next one I want to look at is called the law of definite composition. And you could sort of subtitle that, what's in it and how much. Okay? If you have a chemical compound, no matter where it came from, who made it, it will always have the same composition, meaning the same elements in the same fractions by mass. This is one of the characteristics of chemical compounds. Of course, they have to be pure. That goes without saying. But they have a composition, and that composition is always the same. Right? So let's suppose that we took some of that calcium carbonate that we made on the first slide. We took it down to the laboratory, and we asked Dr. Zaitsev to break it down for us into its component parts. And we already know what three elements are in there, right? Calcium, carbon, and oxygen. And so Dr. Zaitsev, with the characteristic skill that he has, would break this down, and what we would find is something like this, that 20 grams of calcium carbonate experimentally contains 8 grams of calcium, 2.4 grams of carbon, 9.6 grams oxygen, and of course it should all total up to 20 grams. That's what you call a mass analysis. You break the compound down into its component elements and you measure the mass of each one. Now, there are different ways to express this. This is one form of that expression, which we call mass analysis. But more frequently, we will use something called mass fraction or something called mass percent. Now, the mass fraction is based on the idea of each element is present in so many parts compared to one part by mass of the total compound. Okay? And as you can see here, 8 grams of calcium corresponds to 0.4 mass fraction of calcium. How did I get that? Well, you take 8 grams of calcium and you divide it by 20 grams total, and that gives you 0.4. There's no units on this. 0.4 is a mass fraction. 0.4 parts of calcium per 1 part of compound, if you wish. And if you do the same thing for the carbon, it's 0.12, and for the oxygen, 0.48. And if you've done your work correctly, you will find that these have to add up to 1. Okay? And sometimes, instead of using this is sort of a decimal fraction approach, sometimes we would prefer to use percentage. And so you convert mass fraction to mass percent by multiplying by 100%. So that's pretty easy. Percent by mass, 0.4 times 100% would be 40% calcium by mass, 12% carbon by mass, and 48% oxygen by mass. And here, if we did our math right, it'll add up to 100%. So those are 3 ways to express definite composition. And the reason that I show them to you is that from time to time we will need to know what mass fraction means, what mass percent means, what mass analysis means. And it also illustrates the fact that if we took any sample of calcium carbonate, we would get the same results here. Doesn't matter where it came from. If it's pure calcium carbonate, these are the results that we're going to get. Okay, now we can use this information when it's necessary to find out the amount of an element that exists in a compound. That's one of the skills that we need to talk about today. And I'm showing you here that a hypothetical compound XYZ is the focus of our attention. And I have made a definition here of the mass fraction of one of the elements, x in XYZ. It is the mass of x in a sample of XYZ divided by the mass of that sample. Okay? That would be, we would need numbers. We would need this mass, like we had 20 grams of calcium carbonate, and we had 8 grams of, do we have 8 grams? Not already. 8 grams of calcium, sorry. Now, the value of this will become evident in a second. If we wanted to find out how much X there was in some other sample of XYZ, we would take the mass fraction that we calculated up here and multiply it by the new mass, the sample, the mass of the new sample. Okay, because the mass fraction applies to both samples, all samples. Mass fraction applies to every sample of that compound. So if we wish to determine how much gold there was in a sample of gold ore that was a pure compound, we could do it by determining the mass fraction of gold and the total sample mass of the gold ore. Well, I don't have a gold problem for you. I have galena. It sort of looks like gold. It's not really fool's gold. Iron sulfide is fool's gold. This is galena sulfide, and it looks a little goldish there. And here's the problem. We have a 1.27 gram quantity of galena, which I will refer to as G in the future, just to make my writing a little bit more compact. It says 1.27 grams of G contains 1.10 grams of Pb, lead, okay? How many grams of sulfur are present in a 1 kilogram sample of G? Okay, now, as you think about this, you should focus on the previous line here. The previous line says you can calculate the mass of sulfur in a sample of galena if you have its mass fraction and the mass of the sample. Okay, but we're not given the mass of sulfur here. We're given the mass of lead. So there are various ways that we can go about this. I'm going to start it by calculating the mass fraction of lead, and then we'll go on from there. Okay? So the mass fraction of Pb in G is equal to the mass of lead divided by the mass of G. Okay? And we're given the mass of lead at 1.10 grams of lead. Incidentally, do you make it a practice to underline the quantities in problems that you do? Sometimes that helps. If you have no idea how to start, underline the quantities and be sure you know what the units are. Sometimes that alone will be enough to give you a clue as to how to proceed. Okay, but I digress. We're going to divide 1.1 grams of Pb by the mass of the sample that contains it, which is 1.27 grams of galena. And when I did that, I got 0.866 as a mass fraction. Now, what I'm going to do with that mass fraction is figure out how much lead there is in a kilogram, and then I'm going to subtract that from a kilogram to get how much sulfur there. You could have done it the other way. You could have subtracted 110 from 127, got the mass of sulfur, and calculate the mass fraction of sulfur to get the same answer. So here I am. I've got 0.866 grams of lead per gram of galena, the mass fraction, times, now it wants the answer in grams. So I'll start with 1 kilogram of galena times, and there are 1,000 grams in a kilogram of anything. And I will get from that 866 grams of lead, because this was the mole fraction, the mass fraction of lead. So now I know I have 1,000 grams of G minus 866 grams of Pb, and since there's only lead and sulfur in there, the difference will be the amount of sulfur, and I got 134 grams of sulfur. Okay, so this illustrates the use of the mass fraction in determining mass quantities from information like we have in this problem. Does anyone have a question on this one? Comfortable with this? Okay, good. I've got one more here to show you an example of calculating mass percent. A 1.27 gram sample of galena contains 1.1 gram of Pb. What is the mass percent of sulfur in the galena? Okay, the mass percent. So we could perhaps it'd be wise for us to underline that. That's what we want to calculate. So the mass percent is the mass of sulfur divided by the mass of galena times 100%. Okay? So we need to figure out what the mass of sulfur is, and of course we can do that readily because we're given the information that we have 1.27 grams of galena, and in it there are 1.10 grams of lead, and this gives us 0.17 grams of sulfur. So 0.17 grams of sulfur divided by 1.27 grams of galena times 100% is how many significant figures? If we just work from here, how many significant figures? 2. Good. 13%. Does anybody have a question on that one? Okay, good. Then I want to go to the third of the mass laws. Everybody got this copy? No? Hurry along. The third of the mass laws is the most complicated one. It's called the law of multiple proportions, and it applies only to specific kinds of compounds. In the case where we have two elements that combine to make more than one compound, it turns out that in the laboratory it was found that the masses of one of the elements that combine with a fixed mass of the other one are always found to be in the ratio of small whole numbers. 2 times the mass of A, 3 times the mass of A, 4 times the mass of A, but not 0.17 times the mass of A. Okay? Now, these are relationships that deal with the mass ratio in two compounds containing the same element. So a common example of that might be familiar to you is carbon and oxygen. There are, of course, 2 carbon oxides that we are readily familiar with. Actually, there are a number more, but there are 2 nice gaseous ones that we're familiar with. And let's just call them, even though we really know what they are, let's call them carbon oxide 1 and carbon oxide 2. We take these samples of these 2 things down to Dr. Zaitsev, and he says, "Oh no, you again? Be gone. I don't want to talk to you." And he would find out eventually, if we could tell him, convince him to do this, that carbon oxide 1 is 57.1 mass percent of oxygen and 42.9 mass percent of carbon. And of course, since there's only carbon and oxygen, these two numbers ought to add up to 100, and they do, at least to three significant figures. Carbon oxide 2, he would find, have 72.7 mass percent of oxygen, and proportionally less, 27.3 mass percent of carbon. Now, what we're going to do here is we're going to convert these mass percents to mass units. And that, of course, whenever you have to do that, it's very easy because the percents, of course, are out of 100. So if we just take away the percents, and then we'll have 57 grams of oxygen and 42.9 grams of carbon go together and make 100 grams of carbon oxide 1. Okay, so we're going to use the percent values of the two to find the masses of C and O in both compound 1 and compound 2. Everybody comfortable with that? You know how percents work. It's nothing very spectacular there. So I'm going to go ahead and I'm going to go to the next slide and carry this through. So let's take carbon oxide 1 here. The number of grams of oxygen in 100 grams of carbon oxide 1 are 57.1, because it's 57.1% of oxygen. Okay? Carbon oxide 2 is 72.7 grams of oxygen per gram of the compound, using the percents. Okay? And if I do this for carbon, I could do it exactly the same way for carbon. Grams of carbon per 100 grams of carbon oxide 1 will be 42.9. And for carbon oxide 2 will be 27.3. So now I have the mass ratios of the two. And I can go ahead to test the law of multiple proportions here. So what I'm going to do is I'm going to take the mass of oxygen and divide it by the mass of carbon. So I get grams of oxygen per gram of carbon for carbon oxide 1, and the same thing for carbon oxide 2. So it's 57.1 grams of oxygen over 42.9 grams of carbon here, and 72.7 and 27.3 is the ratio over there. And I look at the numbers, and carbon oxide 1 ratio of oxygen to carbon is 1.33 grams of oxygen per gram of carbon. And carbon oxide 2 has 2.66 grams of oxygen per gram of carbon. And here's where the law of multiple proportion comes in, because we're looking at the ratio of the mass of oxygen in carbon oxide 2 to the mass of oxygen in carbon oxide 1. They're both referred to 1 gram of carbon. Okay? So dividing this ratio in 2 by that in 1 gives the small whole numbers I was telling you about. 2.66 over 1.33, small whole number 2 over 1. Okay? Now, this holds for any set of compounds that are composed of the same elements. And it can get sort of complicated if there are 4 or 5 elements involved. So we'll focus on, in most cases, 2 different elements in a compound. Does anybody have a question about how we arrived at this? Does it make sense to you? Okay, don't see a question. Yes?
Do we always put the larger number on top?
It is, he asked if we always put the larger number on top. It is conventional to do that, so we normally would do it.